depending upon the compressive strength, your tensile strength can range from 1.5 to 2.5 or 3, or usually, like we said, it is about 10%. And with fiber addition, depending upon the fiber volume fraction that you will have strain softening or strain hardening behavior, right? But in you can see here in UHPC, you can get as high, if you look at it again, the tensile strength is function of your compressive strength. It is usually 10%. You can get as high as 8 to, in fact, 20 megapascal in tension as well. So you get a very high tensile strength, and again, it doesn't give away very quickly right after cracking in tension. So it is going to offer some post cracking tensile resistance as well. So if you try to zoom in this behavior, you can see here that the strength drop at the strain levels of as high as even 0.06 is not that much, because the fibers are bridging the cracks, and it is offering you quite a big tensile resistance. So when I'm trying to use this, then usually in a regular concrete, if you've done flexural design, what we really do is, we ignore the contribution of concrete in tension. But if you are able to get like 7 to 8 megapascal of tensile resistance, then the tensile resistance of concrete below the neutral axis need not be ignored. So it is going to give you very good resistance in tension also. So that is going to improve your bending moment resistance and crack resistance and so on. So this is the advantage with using this very high strength material. Right. So now let's look at what are the advantages of UHPC. Of course, we talked about strength and ductility. So for a particular strength and for particular serviceability criteria that what I'm designing, I can design the member with very small cross section, and because this UHPC bonds very well with the reinforcement. So for reinforcement, you really need only very short development length. And most importantly, you have a very dense mix. So your deleterious substances like chloride, sulfate, and all these kind of salts, it cannot really get into the concrete and reach the level of reinforcement. So then only the starts, right? So because I'm not allowing this deleterious substance, then you end up with higher durability and longer life. So these are all some of the advantages, and most important also, like what you see here, these are some of the bridge deck constructions, and these are all precast panels, and these precast panels are put on top of these steel girders. Then what they do is, they connect these joints. You can see that these bars will be connected together, and in these joints are made using this ultra high performance concrete. And you can see here that here you really don't need any vibration. So it is a self consolidating concrete. So you don't really need an external vibration to consolidate your concrete. So that's also another big advantage with self consolidating concrete. So to achieve this self consolidating concrete, we are talking about a flow of like 200 250 mm flow. To achieve that kind of a flow, then I cannot really use a large size aggregate, because you can also see the spacing between this reinforcement is very, very tight. So usually in UHPC, the coarse aggregates are not used. Even fine aggregate, the size of the fine aggregates is limited. That's why we are able to achieve this self-consolidating nature of this concrete. And several testing has been conducted, especially for bridge girder applications, where you are going to have a very high loads and we want to go for a very large span. So then this kind of UHPC based beams becomes very, very attractive. Already a lot of research has happened, and these are some of the references that you can look at it. And because of the self-consolidating nature, I can also make shapes of very complex shapes. Okay, and I can also end up with, for the architectural purposes, for facade panels and all, can be made with very lightweight, with very light thin elements, and we can also create different surface structures. So these are all some of the advantages of ultra high performance concrete. But of course, this is also has disadvantages, because we are going to use very high amount of cement. So the cost of this UHPC usually it is about 10 to 15 times, depending upon how you, again, you gain all these advantages, but the cost is going a little bit on the higher side, right? Yeah. So let's look at, now let's compare, just a quick comparison, not only about the mechanical properties, but also about other properties. If you start comparing the properties of UHPC with conventional concrete, like I said, again, compressive strength for conventional concrete, you're talking about 20 to 50 megapascal. And here UHPC, we are talking about more than 120 megapascal. And tensile strength, like I said, 10% of compressive strength. So you're talking about tensile strength of 2 to 5 megapascal. Here you're talking about more than 12 megapascal. And modulus of elasticity for a conventional concrete anywhere ranges from 20 to 30 gigapascal. And for UHPC, because you are having a denser concrete mix and higher compressive strength, so your elastic modulus also is going to be very high. So it ranges from anywhere from 40 gigapascal to 60 gigapascal. Obviously, when the elastic modulus is very high, then you end up with a very good flexural rigidity. So you can basically come up with design a very sleek, very slender cross sections for the external load to be done. This is also an important parameter. If you see shrinkage, conventional concrete, most of the shrinkage that happens from long-term shrinkage. It is not from short-term shrinkage at the early age. Most of them that happens from long-term shrinkage. And here you're talking about 500 microstrains. UHPC, because we are using a lot of cementitious material, so your shrinkage strain is going to be larger, because aggregates are also, we are not using coarse aggregate. So shrinkage is an issue. But however, because we are putting a lot of fibers, that the cracks will be arrested. And if you see here, the microstrain in UHPC, we are talking about 500 to 1000 microstrain, depending upon your mix design. But most of these things happen at early age. So you're not going to have any long-term shrinkage. And from durability point of view, people have studied that chloride diffusion coefficient, you're talking about in the order of 2 into 10 to the power of minus 11. But UHPC, because you're having a very dense concrete mix and you have nice particle packing, so you're talking about almost 1/100th of what we have for the normal concrete. So obviously the chlorides cannot diffuse, so the corrosions cannot happen, right? So you end up with a very good durability. Similarly, freeze thaw resistance and other things, dynamic modulus after 300 cycles of loading, that what we have said is relative, it is more than 95 plus. So it's much better than the conventional concrete. So these are all some of the advantages of ultra high performance concrete. And we also have UHPC in bridge girders. For example, as concrete is one of the most preferred material for construction, even in bridges, mostly in the medium span. Like, when you talk about spans up to 30 meters or 40 meters, usually we go for these kind of box girder or post tension girder systems. And of course, in bridges, you're talking about very heavy vehicle loads that will keep going. So when we do pre-stressing, what happens is, this is with a regular concrete. You end up, compressing at the end anchorage zones, very high amount of force. So when you put that kind of a force, what can happen is the end zones can undergo, if you don't design it properly during pre-stressing, the anchorage zones can fail, right? Because it's not able to take care of the tensile stresses that is happening, because though you're applying compression on the lateral side, you're going to have tensile stresses. So if you're not designing properly with adequate reinforcement, then these kind of failures can happen. And so for such kind of scenario, for very heavy loads, even for applying pre-stressing, then ultra high performance concrete becomes a natural choice. And you see here that these are all some of the pre-stressed concrete bridge girders that has been done. There's a company called UHPC India. So they have done this. They've used it in bridges as well as in some building applications. And in Graz University of Technology, they have also developed these kind of a very sleek girders. for using ultra high performance concrete. This is again, just we are comparing different types of systems: reinforced concrete, precast concrete, and this is steel, and this is ductile, which is a proprietary ultra high performance concrete system. And you can see here that using UHPC, we can end up with the same, similar cross section as that of you have for structural steel. So this is a very big advantage with the ultra high performance concrete. Yeah, just a quick history of ultra high performance concrete. As you all know, the basic Abrams rule. Usually, when you have very low water cement ratio, and in a conventional concrete, we try to use water cement ratio anywhere in the range of 0.3 to 0.4. But actually, for hydration process, you really need only about 0.15 or so. So rest of the water, basically, it sits idle, and it creates a weak link in the concrete. So what happens is that it reduces the density. So this is for two types of concrete: air entrained concrete and non-air entrained concrete. And as you can see here, as the water cement ratio is increasing, you can clearly see here that the 28-day compressive strength keeps reducing. So if you want to have a very high strength concrete, the first thing that what we need to do is we need to use very low water to water cement ratio or water to binder ratio. Right. So when you put very low water cement ratio, then you end up with a greater density of concrete and higher strength, and also the permeability of the concrete is going to be low. So this is basically the basic Abrams rule, and it was, in 1920s itself, it was formed. Right. So then from 1970s to 1990s, people started, using, because of the advent in the chemical admixture technologies, people started developing these chemical admixtures. So these are also called as high range water reducers or water reducing admixtures. So because of that, we, even with very low water cement ratio, we were still able to achieve the workability. So a lot of development happened, and high strength concrete came into picture from 1970s or so. And this also happened because, we were also, commercialization of silica fume happened around that time. So silica fume is a very, very fine particle. So again, by adding them into the regular concrete mix, basically I can densify the concrete mix so that I can end up with a very high strength concrete. And then I would say from 1990s onwards, I think, people started not only about high strength, people started talking about high performance, because strength is not the only criteria. We also need to look at durability and sustainability and so on. So people started using a lot of the supplementary cementitious material, including fly ash, GGBS, and silica fume and so on. So with the lower water cement ratios and by adding specialty admixtures, people were able to develop high performance concrete, which produces very high strength. Also, it produces a very dense microstructure, and it is with very low permeability. So that development happened around 1990s to 2000. I would say around the same time, also from 1990s, people also started developing what is called as a reactive powder concrete. So that is what it is. Nowadays, it's called as ultra high performance concrete. Again, the whole idea was from the basic Abrams law. You use a very low water cement ratio, and by using specialty admixtures, and also you carefully choose a range of particles so that you can really pack them well. So using particle packing, so using silica from supplementary cementitious materials and fibers, now we can achieve strength as high as 150 megapascal, and tensile strength as high as 15 megapascal. So this I would say last 15 years or so, a lot of applications people have used this ultra high performance concrete. And this is one of the first ultra high performance bridge that was constructed in Wapello County in the state of Iowa in United States. So this is just a brief history of ultra high performance concrete. And so now let's look at how do we really, make this ultra high performance concrete. So when we said ultra high performance concrete, as we know, we have self-consolidating concrete where, the material can flow on its own and doesn't need external vibrations. The flowability is very good. And with fiber reinforced concrete, we know that by addition of fibers, we get very good strength improvement in tension, as well as you get a very good ductility. And in the high performance concrete, what we do is we use supplementary cementitious material and we densify the concrete, so your durability properties are improved. So if you can we develop a material that combines the advantages of SEC, FRC, and HPC. So that's how basically this thing came, which is that's basically the ultra high performance fiber reinforced concrete. And what we have here is in UHPC or UHFRC. Here UHFRC means ultra high performance fiber reinforced concrete. We are talking about what are the basic components. We are not talking about cement, of course, fly ash. We are going to, of course, use water for hydration. We cannot completely, and we are going to use a lot of super plasticizers, and we are going to use fibers. Mostly they are steel fibers, and they are, and then we are going to use sand of different mean particle size. And we are also going to use GGBS and silica fume and so on. So these are all some of the basic components of the UHPC mix. When you look at your normal concrete, if I'm looking at 100 size, if you look at it, usually, if we say that we are using a 20 coarse aggregate size, and you can see that in between the spaces are filled by these smaller particles. And UHPC, what we are saying is, we are not going to use aggregate size of 20 In fact, the aggregate sizes will be limited to 3 or 4 which is basically your sand. So when you look at it at a very small scale at this 20 you can see here that a lot of these white spaces are all gaps. Okay, these are all pores. But here, if you look at it in a smaller scale, in UHPC, what we are having is we have different particles. Okay, so that is basically including cement, silica fume, fly ash, sand, GGBS, and so on. You see here that the gaps in this system is very, very small. So the particles are very well packed. So obviously, when particles are very well packed, you end up with a very high strength. And also, we are going to use a lot of cement, and the cement is going to basically react. And all this reactivity of all the other materials also will be used by the cement, and then cementitious products will form, and you get very high strength. So the whole objective is basically we use particles ranging from 0.01 micron to almost 4,000 to 5,000 micron. And what we really do is we really pack them really well, and we achieve a very dense concrete that is going to give me very good mechanical strength as well as ductility and durability. So that is the idea. So basically, the particle packing is the essence of developing ultra high performance concrete. Like again, what are the typical UHPC composition? So if you look at your conventional concrete, as I've told you, coarse aggregate we try to use for reducing the shrinkage and reducing the cost, and also for getting dimensional stability. And if you look at the weight, almost 43% of the weight of conventional concrete, this is range. Maybe we can say 40 to 50% of the weight is occupied by coarse aggregate, and about 15% of the weight is occupied by cement, and 7% is occupied by water, and about 35% is occupied by fine aggregate. But if you look at the compositions of the ultra high performance concrete, we are completely have got rid of this coarse aggregate. And even in fine aggregate, I'm going to limit the size of the fine aggregate, and I'm going to have gradation. So if you can see here, the fine aggregate percentage of weight is maybe 35, it has increased 41%. So somehow I have to account for this weight of coarse aggregate. So for that will be replaced by finer materials like cement. Cement is always there. I'm going to put more cement. In fact, we put cement in the order of 800 kilogram per meter cube. In a conventional concrete, we put a cement anywhere ranging from 250 to 400 kilogram per meter cube. So we put a lot of cement because it's a very fine particle. And we also going to have silica fume, and we are also going to have other supplementary cementitious material like GGBS or sometimes very, very fine sand as well. Right, so this is your typical, and also we end up putting a lot of super plasticizers. So super plasticizers usually, we put like 1% to 2% by weight of the cement. So this is a typical composition. Of course, we add lot of these steel fibers, or sometimes we use also combination of steel fibers and some synthetic fibers, and we add water and high range water adhesives. So all of them combined together, you form this ultra high performance concrete. Again, commonly used fibers, we have different types of fibers can be used, and most commonly used fibers are the macro fibers. Usually the diameters ranges from 0.2 to 0.3 mm, and length we want to keep it relatively short, and usually we use hooked end fibers of 13 mm length, which is commercially easily available in the market. So that's what we try to use. However, we can also use, you can see the diameter 0.18 12 mm, 13 mm, 0.2 mm diameter. So like that, different things. But usually we try to keep the length to less than 15 mm. And we can also use other synthetic fibers like polyester, polyethylene, polypropylene, and different combinations. But steel fibers have, because of its stiffness, they can arrest crack widths at a very low crack widths. So they are becoming more efficient. We can also look at hybrid combinations of all these fibers. So that is also possible. Right. So now let us look at what are the material design aspects of ultra high performance concrete. Of course, by using locally available materials, we can develop a rational binder design based on the performance what we need. So the performance are usually, we need good compressive strength. You can target a compressive strength of 120 or 150, and we can also want to reduce the cost, and we also need to look at the workability and durability and so on. These are all some of the parameters that you should fix first, and then optimize the mix design. And how do we optimize the mix design? Of course, by optimal packing of the particles and making sure that you have necessary reactivity. And then we also have self-compacting flow, because this is also one of the important aspects of this UHPC, because the flowability or self-compacting flow is also one of the important parameters. Again, design. And like I said, the aggregates are inert materials, right? The shrinkage happens only in the cement paste, right? When the cement is hydrating, that's where the shrinkage is going to happen. So as much as aggregate, if you try to use, it will provide dimensional stability and it will reduce the shrinkage. However, larger size aggregate, then it will compromise the self-compacting nature of the concrete. So we have to balance all these properties and then appropriately design the material mix. So again, the mechanical properties, of course, we need to conform it with the design requirements what we need. So we need to target first, okay, I'm looking at compressive strength of, let's say, 120 to 130 megapascal, and I am going to use locally available materials. So, like fly ash, GGBS, whatever that we using the locally available material. And I need to have a minimum tensile or flexural strength. And cost, of course, cost is an important parameter. There are also a lot of proprietary this UHPC mixes are available. Like I said, the cost of the systems are 15 to 20 times the regular concrete. So again, for larger applications, for a conventional common applications, then cost becomes a very important parameter. Unless you are talking about a very niche application, cost is not an issue. But most of our construction, it's bound by cost. So that again, we have to look at all these aspects. Okay, so there are some design guidelines that are available. Preliminary guidelines are available in Canada, France, Japan, and so on. However, we need to have more research is still required for developing simplified procedures for developing mix design. And whenever for a certain project requirements, the specifications have to be given. So that would be depending upon the application for which you are going to use the HPC. So it will be project specific. And in the United States, of course, there are PCA, Federal Highway Authority, and ACE. They all joined together. They're funding a lot of research. And these are also some of the reports that are FHW reports are already available. And we also have an ASTM. And usually, like we said, how do we design this UHPC? Usually we do sequential trials, and nowadays also we use, there are some particle packing models like this. If let's say that I'm going to use, for example, these are the three, let's say sand, cement, and silica fume. And if you're able to from particle size analysis, if you're able to find the distribution of these particles, then in the mix, depending upon how much weight that I'm using, you can also come up with using the weight fraction, you can also come up with a combined distribution for all the mixes together like this, right? Then we also have this particle packing model. One of the popular one is this Anderson model. And here what we have here is D is basically the particle size, and Q is basically a factor which is called as a shape factor that from 0.19 to 0.37 for ultra UHPC. Have a very small size, that what I have is a 0.1 micrometer. So your D minimum is going to be 0.1 micrometer. And then here we are talking about, sand, if you talk here about, you have about like 1,000 micrometer is the largest size. So D max is 1,000 micrometer, D minimum is 0.1 micrometer. So you can also come up with basically this, depending upon how much volume that you have for all this ingredient that you've chosen, you can also develop this. If you combine all of them, what would be this, the particle size distribution, right? So that we can develop using this model. Right. So in addition to that, like I said, for UHPC, strength is not the only criterion. The flowability is also an important criterion. So basically, we try to use this flow table, and it's basically a mini slump cone arrangement. And we put our mix in here, and we try to see how much it is really flowing. And usually, we target about 200 to 250 mm flow for this UHPC, even with the addition of 2 to 3% of fibers. In addition to the flow, then once you're happy with the flow, then we also need to make sure that the compressive strength and tensile strength, compressive strength, of course, we test it using cubes or cylinders. We can test it and we can find what is the strength. And splitting tension test is relatively easy to do for understanding the tensile test, tensile strength of the concrete. In splitting tension, what we really do here is we cast a cylinder and we put it in the transverse direction and apply a line load. So when you apply in compression, what happens is the middle portion of the middle cross section will be subjected to tensile stress. So based on the load at which it is failing, we can calculate the splitting tension test. It's also called as Brazilian tension test. So from this, we can indirectly get the tensile strength. Though you're squeezing it in compression, basically you're splitting it by applying tension in the transverse direction. So that's why it's called a splitting tension test. So using this, we can also get what is the tensile strength of concrete. And for research purposes, people have also tried this direct tension test. And when we want to do such high strength concrete under tension, it is relatively a very difficult test to perform. We need to have a very good servo control system to control the cracking, and we need to have a very high stiff system. And usually what people do is people embed these bars and strengthen these end portions, and they make it, that's why you see here the test region is small, the end regions are very high, and then you attach a bar, then you pull on the bar. So the middle portion, which doesn't have any reinforcement, will be subjected to pure tension. So you get the tensile strength. Then you study what are the performance of this concrete under direct tension. Right. So like I said, we talked about strength, what are the properties that we need to do, and flowability. Of course, we need to do slump cone test when you're developing a mixed design. So we need to make sure that they're satisfying. In addition to that, durability is also an important parameter. And one of the quickest tests that we do is a rapid chloride permeability test, RCPT test. Basically, RCPT test, it measures the charge that is passed through a concrete sampler under a constant applied voltage. So if the higher the charge is passed, basically what we are saying is the concrete is more porous and it is allowing the chloride to ingress and create damage. Okay, so for example, if you see here, these are some of the results that I have taken from Professor Narayan and Naithlet presentation. So you can see here that in conventional OPC concrete, you get a charge passing of as high as 4,000, so which is very, very high, and that indicates that the chloride the concrete is permeable, and basically it is allowing a lot of charges to pass through. But as you go to high performance concrete or UHPC, you can see here that now you have densified the mix by using supplementary cementitious material. So the charge passing is reduced from 4,000 to 1,000 for high performance concrete. For UHPC, you get as low as 500 or so. So you can see that almost 10 times it has reduced. So that means that my durability performance or the UHPC is also going to be 10 times more durable than that of ordinary Portland. Various other tests that are available for assessing the durability parameter. Now let us also look at what are the various applications. As you can see here, now it's very common to go for exposed concrete so that you don't really need painting. You can achieve when you go for ultra high performance concrete, and these are all some of the locations like Church of Light in Japan. These are same project outside and inside, and we can also see here, these are all some of the structures that have been built, and there are a lot of facade elements with all this nice architectural features. Still they should be able to transfer all the load, so that can be, and you can see these are all very thin sleek elements with the complex shapes that can be made using this UHPC concrete. So, and now people have also started developing these other products using ultra high performance concrete. And you can see here that concrete lighting, this casing is basically made from UHPC. And you can make complex shapes using ultra high, because it's a very flowable concrete, is a very high strength, and by very thin cross sections, you can, it's not going to be very heavy. So these kind of concrete lighting products have been developed. And you can look at this chair. This that has also been developed using ultra high performance concrete, and it's very durable, right? So, and it is going to take care of all the loads, because we are talking about a very high tensile strength. And so you can see the thickness of these legs and then the resting places, right? So it is very, very thin. So these kind of innovative products also can be made using this ultra high performance concrete. And most common applications, of course, in bridges, where, like I said, to speed up the construction, people are now going for precast construction, or in the US, they call it as accelerated bridge construction. Now, most of the elements are made in the factory, then they just brought it to the site, they erect it. And then what they do is they need to join the elements together. Of course, when you join the elements together, connections have to be very, very nicely designed. And for connections to be very robust, then you need the bar, because it is having very high tensile strength. It is able to transfer all the forces, and also because it has a lot of cementitious content and fine powder content. So basically, the development length for these bars also can be quickly achieved. So that is also another big advantage of going for this ultra high performance concrete in bridge applications. Right, now I'm coming to the main topic, which is application concrete in blast resistant design. As we all know that structures undergo these kind of explosions, maybe due to war in conflict area, or this is our famous Taj Hotel attack, due to terrorist attack, or maybe due to the vehicle impact. So all these things basically subject the structural element to very high uh, impact loads, right? So, but among the materials available, concrete offers very good temperature resistance, and also it provides some mass and flexibility in detailing, because I can detail the reinforcement so that we can in a blast, what happens is when you have an explosion like this, you have these kind of shock waves that are created, and they travel in a hemispherical shock wave that keep traveling, and then they go and hit the structure, and you create what is called as overpressure and reflected pressure. So that is basically going to damage the structure. These structural elements are subjected to very high strains under the action of this shock waves. So we need to understand the behavior of this material. Basically, reinforced concrete we are using, we need to understand the behavior of concrete under these shock waves to see under high strain rate how these systems are behaving. So in a typical, you can see this is one of the damage of the building after the blast. And during a blast, of course, explosion happens, and in explosion, basically it is a rapid process of rapid energy release, basically, which generates a blast pressure wave. And this pressure wave travels in, like what we've seen here, in a creates this hemispheric with this basically the pressure wave will propagate radially through air, and then basically they go and impinge on the structure. And when this pressure waves are impinging on the structure, the structural members undergo very high strain rate under the impingement of the pressure wave. So for such a kind of very high, they're subjected to very high shock wave or pressure wave. These blast resistant designs should have very high strength, ductility, and also it should be able to absorb the energy. So if you look at the pressure distribution, what you have is it's a very short, pulse. So it happens over basically a millisecond. Okay, you have a sudden increase in pressure, and then this pressure basically dies down. So this we call it as a positive phase. And you also have a negative phase, because you always have an ambient pressure, atmospheric pressure. So, but it will go below the ambient pressure. So this is basically an impulse is basically the integration of the pressure over this time. So this area under this pressure wave, pressure time curve is basically is a specific impulse. And again, it is a measure of how much is the how much is the energy that that structure is particularly subjected to. Right. So again, what happens, why then again, why that blast resistant design? Like we said, usually in case of a blast wave, this travels in the form of a hemispherical wave that we said. And usually it goes, and the pressure wave goes and attacks the exterior wall, and then it can damage these columns. And also what happens is, once these elements are penetrated, then you also have the floors will be subjected to upward pressure. And then once that is also getting damaged, basically then you can, it is basically it's going to surround the entire structure. Then you can also create downward pressure on the roof. So it can lead to the complete collapse of the structure itself. So for a good blast resistant design, what we need to do here is we need to suppress in concrete. When it is subjected to that kind of a shock wave, the concrete material under high strain rate can fall off. So we need to suppress this falling of the concrete and also the scattering of this concrete fragment. So how do I do that is basically by adding fibers. Addition of fibers will help to reduce this falling of the concrete and scattering of the concrete segments. And especially for high-rise buildings and plant equipment, the local damage caused by these explosions can lead to continuous collapse, like what we have seen. First it goes, it happens in a very progressive manner. So it can lead to localized damage also can lead to continuous collapse, loss of life, and property damage. So again, so under this action of this blast loads, what happens is these materials that we use for constructing the structure, they undergo a very high strain rate. So they are subjected to very high strains at a very short span of time, right? So So the strain rate usually, it is a function of specimen length. For example, if I'm testing a specimen, when we say deformation, we say that you apply deformation at a particular rate. So that is basically, when you test it in a universal testing machine or a Rafetic testing machine, you apply the load, and it is basically measured in the form of the cross-head movement of the machine. But when you talk about strain rate, it also is function of the specimen length. Usually short specimens can stretch more during the same time period than a long specimen, because because if you keep the same strain rate, shorter specimens will undergo larger stretching than the longer specimen. Okay, so what is the strain rate? I mean, why should we concerned about strain rate? Because in blast, the materials that are used for constructing the structure, they undergo very large, very high strain rate. So what is the strain rate? Strain rate is a rate of change of strain with respect to time. And this is what it is. And usually what we do the testing in our lab, they are all quasi-static loading, and we apply the loads at a very small strain rate. So, you're talking in the order of 10 to the power of -6 to 10 to the power of -5. So this is a range of strain rate that we apply usually in structural testing under static case. And creep is also, it happens very, very slowly. So there the strain rate is, you're talking the order of 10 to the power of -9 to 10 to the power of -7. And when the vehicular impact, you have a strain rate of 10 to the power of -4 to 10 to the power of -3. However, in the case of blast, depending upon the strength of the explosive, the material can undergo strain rate anywhere from 10 to the power of -1 to as high as 10 to the power of 4. So these are the very high strain rates, because this is the normal static range. You can see here 10 to the power of -6 to 10 to the power of 2, 10 to the power of 4 that we are talking about. So multiple orders of high strain rate that materials are undergoing when you have a hard impact or a blast. So that the way the system behave is going to be very different. And these are between quasi-static and very high strain. So these are intermediate strain rates domain, and these are basically high strain rate domain. Right. So what are the effect of temperature and strain? As we have seen, it is also one thing. When I'm subjecting the material to high strain rate, what I also get is a high strength. There are some dynamic factors that are involved. Okay. So, but at the same time, when you have a temperature also, what happens is temperature starts degrading the strength. If you look at it, a very small strain rate, 10 to the power of -4, at 30 degrees centigrade or a room temperature, let's say the tensile strength is, about 200 megapascal. Okay, but as the increases temperature, you can clearly see here that the strength will come down. Of course, the temperature will soften the material, and it will also weaken the material, so it is going to fail at a lower strength. It can fail as low as 10. But if you look at a very high strain rate, you can see here that again the same phenomena is there. However, you can see here that at a high strain rate, the strength is higher than what you are getting it at a low strain. Okay, so again, because of the dynamic application of the load, the material strength also increases. So that also we have take into account. Right. So how do we test this material under high strain rate? Usually, when we do slow static test, we use servo-hydraulic machines, and that can apply strain rate, like I said, in the order of 10 to the power of -6 to 10 to the power of -3. And we can also test material using drop weight impact testing. There we can generate the strain rates in the order of 1 to 10. But with the split Hopkinson pressure bar setup, we can test at a reasonably high strain rate in the order of 100 to 1000 also. So depending upon the setup that what you have. So this is one of the drop weight impact testing machine. And this is the split Hopkinson pressure bar testing machine that we have developed in our lab. So that is it's located in IIT Hyderabad, and it is also one of the longest. And you can use it for testing concrete composites at very high strain rate. Again, so the mechanical properties of concrete under dynamic loading under very high strain that are going to be very different than that of static loading. And both strength and stiffness of the concrete under dynamic conditions will be higher than that what you get in static conditions. So this increase in the strength, we call that as a dynamic increase factor. And dynamic increase factor is dynamic compressive strength divided by static compressive strength. And if you look at what is the effect of strain rate, so if I'm testing the material at a different strain rate, so if I'm testing it at a very low strain rate, like what we talked about, 10 to the power of -2 to 10 to the power of -3, this is your static test. If I take a concrete cylinder and I test it, I get a strength. For example, this concrete has 100 megapascal, and then it reaches its strain at about 0.0025, and then it starts degrading. For the same concrete, if I test it under high strain rate, 49 or 97 or 323, you can clearly see here that the elastic modulus of this material increases, and also strength also increases. So because of the dynamic load application. Right. So, and FIB code also gives you some factors for concrete to calculate your dynamic increase factor, because dynamic increase factor is it's easy for me to quantify, how much is the strength that particular material can take under high strain rate. So already people have done a lot of testing and they've calibrated these equations, and you can see here that as the strain rate is increasing, the dynamic increase factor is also increasing. So it anywhere ranges from, for a strain of, let's say, about 10, you have about 1.5, and then it goes as high as 2.3 or so. So that is also one of the reasons. So the basically high strain rate, under high strain rate, basically you get a very good strength improvement that we call it as a dynamic strength increase factor. So that it is going to increase with increase in strain rate. And people have also tested different concrete, and they have given this dynamic increase factors. You can see here, like I said, if you are in the slow regime, 10 to the power of -5, 10 to the power of -4, or 10 to the power of -3, you can see here that the ratio, the dynamic increase factor is very close to that of 1. So that means if I'm applying strains at a very low rate, there is this dynamic increase factor, there is no increase in strength. So either I apply 10 to the power of -5 or -4 or -3, more or less it is lying close to that of 1. The moment I am getting into the range of strain rate in the order of 10 to the power of 0, that is 1 or 10, you can see that the dynamic increase factor increases, that increases to as high as 1.6 or so. At higher strain rates, when you talk about strain rates in the order of 100 or 1000, you can see here that the dynamic increase factor increases rapidly. The dynamic increase factor for a strain rate of 1000, it goes as high as 3.5, 3.6. So higher the strain rate, higher will be your dynamic increase factor. Okay, so this is the setup that what we have created. So this in split Hopkinson pressure bar setup, what we have here is a pressure accumulator, is also called as a gas gun, and you have a double acting valve. So you build pressure in this accumulator, you compress the air basically, and then when I suddenly release a valve, right? So basically you have this called as a striker. So basically, just like in your gun, you put a bullet, right? So in the same way, this striker is like a bullet. So because of the sudden release in pressure, it is going to push the barrel, and that push the striker. The striker will come at a high velocity and it will hit this incident bar. And then you have specimen will be usually is sandwiched between the incident bar and the transmission bar. So you impact this incident bar. So you have these, when you are impacting a material, you generate this compression stress waves. The stress wave travels and then travels through the specimen. At the interface, some waves will also get reflected and goes back, and then some waves will get transmitted to this transmission bar. So you measure using a strain gauge, you measure what is the strain history and the incident bar and the transmission bar. So using the one-dimensional wave propagation theory, I can calculate what are the strains that I am applying on this specimen. So that we can see, and we put the strain gauge and use oscilloscope to measure all the strain. Right. So basically, it consists of a gas gun. Like I said, this system is a gas gun, a bar system, and a data recorder for recording all the data. And gas gun composed of pressure accumulator, a double acting valve to release the pressure, and a barrel. Then inside the barrel is where you have a striker that is going to go and hit this incident bar at a high velocity. And now between the striker and this, you also have put what is called as a pulse shaper to change the shape of the pulse that what we are creating. So bar system composed of striker bar, incident bar, and a transmission bar. And usually strain gauges are installed in the middle of the incident and transmission bar. Now let us look at, and you specimen is sandwiched between the incident and transmission bars. Now this is just the schematic of what happens. Like I said, when the striker bar is released, it is going to go and hit the incident bar, and it signal. Okay, the compression wave is going to travel, right, and you create this signal. Okay, when I'm measuring it, then what happens is some portion of this you can look at here. So this is the incident wave, and then it gets reflected, some of them. Then it also gets transmitted to this transmission bar. So using these strain histories that I'm measuring on this incident bar and transmission bar, and I can calculate what are the stresses that I'm applying, stresses and strain rate that I'm applying on the specimen. Right, so this is basically once the striker hits the incident bar, you are basically creating this longitudinal compression waves. So the particles in these bars are going to move in this direction, and for this, usually the stress waves are assumed to travel. The wave propagation is described using one-dimensional wave propagation theory. And for this, we design these bars to be remaining in elastic. So we use a very high strength bar. Compared to the strength of the specimen, the strength of the bar is going to be 20-30 times larger than the specimen strength. And the bars are assumed to be remaining in elastic case. And when the stress pulse is propagating, the bar is assumed to be remaining in elastic. And we also need to ensure uniform axial distribution over straight, and the inertia effects also we need to reduce it. And the incident bar specimen interface and the specimen transmitter bar interface has to remain plane. That means they have to remain straight or flat all the time. And when these waves are traveling through this incident bar and through the specimen goes into the dynamic equilibrium. And when the stress or force across the specimen becomes, it will become constant after initial phase of oscillating stress, which we call that as a ringing up stress. So after 2, 3, 4 such reflection of these stress waves, the specimen will get into dynamic equilibrium. Okay, so initially there will be some oscillating stress. You need to have at least 3, 4 stress wave traveling, and then the specimen will come into dynamic equilibrium. And we also need to make sure that the friction between the specimen bar interfaces and inertia effects in the specimens are completely negligible. So using that, like I said, we also need to make sure that the lateral dispersion of the wave should be very minimal to make sure that the assumptions of one-dimensional wave propagation is valid. And also the stress distribution should be uniform across a cross section of the bars. So that means there is no radial dispersion in the bars. And the accumulated strain in the specimen is calculated solely based on single incident stress pulse. So whatever that we are hitting, that striker comes and hits, we assume that the strain accumulated in the specimen is only because of this single incident stress pulse. So that is also another assumption. Now this is what we really do here. If you look at the incident bar and transmission bar, and your specimen is here. So I measure from the incident stress pulse, I get this strain, and then after getting reflected stress pulse, I get this reflected strain, and some of them travels through this transmission bar. That strain also I measure, right? So if you look at the interfaces of specimen with the incident bar and the transmission bar, then we can say that we have seen in this, I'll go back. Yeah, if you see here, so this is the particle motion, right? So yeah, so this is the way the wave is propagating, but particle is oscillating like this. So so if you look at the particle velocity at this interface, so I can calculate the particle velocity at the specimen input bar interfaces. This is wave propagation speed times epsilon I minus epsilon, because this is one strain that is going, it is coming the opposite direction. You subtract it and you calculate with the wave propagation speed. Then I get my velocity at this interface. Similarly, I get the velocity at this interface by wave propagation speed multiplied by the strain, so epsilon t. And now, what is the average strain rate in the specimen? I know the length of the specimen Ls. I know the velocity at this location is V1. I know velocity at this location is V2. So the difference in velocity divided by the length will give me the strain rate. So strain rate is what? Basically the deformation by time, right? How fast you're applying the deformation. Velocity is also same way. The particle velocity is also same. The particle is moving at a speed that I am dividing by the length. So basically I get a strain, how fast the strain is getting applied. So if you subtract these two, then you get an expression in terms of epsilon I minus epsilon R minus epsilon T divided by Ls times the wave propagation speed will give me average strain rate in the specimen. So similarly, like we said, that specimen has to be in dynamic equilibrium. So the forces on the left side and right side has to be equal. Then only the equilibrium condition will be satisfied. So I can calculate the stresses from the area of the bar and area of the specimen. I know the elastic modulus of the bar because Hooke's law is valid, because this bar and this bar is always going to be remaining in elastic state. So I can calculate the stress at this interface by AB by AS times EB times. This is the total strain that the particular bar is undergoing, because everything is in equilibrium. So this, whatever that stress here at the interface should be valid here. So we calculate sigma 1. Similarly, sigma 2 also we calculated, but to achieve the stress equilibrium, I need to have sigma 1 should be equal to sigma 1. So when I'm equating this, then you will get a condition that the incident strain and the reflected strain, when I add them up, that should be equal to the transmitted strain. So again, from here, from this condition, when I substitute epsilon I plus epsilon R into this strain rate equation, then strain rate, average strain rate will become minus 2 times CB by Ls times epsilon R. And from this one of this equation, of course, we can get your stress. Strain rate is there. If I want strain, what I need to do? Strain rate is basically strain by time, right? So I need to integrate the strain rate from particular duration to get the strain. So I get both stresses and strain. So this is the way I get the stresses and strain in the material. So for now, of course, it's not really straightforward. When you design the split Hopkinson pressure bar setup, we need to be very careful about a lot of factors. First of all, the selection of the rods has to be proper. We need to have a very high strength bars, so that these kind of when this thing is happening, this there should not be any indentation on the specimen incident bar or as well as on the transmitted bar interface. So that is not allowed. So the bar should be within elastic range at all times. End surfaces should be flat and parallel, and the ends may get, if I do repeated these kind of impact test, then the end surfaces may get indented while doing testing of concrete with extremely high strength. So the bar should have sufficient strength to avoid indentation. So that is one thing that we need to make sure. Now, how do I select the diameter of the specimen and rods? The specimen diameter should be large enough to accommodate the size of the aggregate. If I want to use this facility for testing a normal concrete, and in normal concrete, we know that the aggregate size that what we use is about 20 mm. So if I'm putting 20 mm aggregate size, to consider to be the material to be uniform, at least I need to have 3 to 4 times the size of the aggregate should be my specimen diameter. Then only I can, in an overall sense, we can assume this to be homogeneous. And the minimum diameter of the concrete specimen also, that's why, if you're using 20 mm, at least 3 times, right? So 3 to 4 times. That's why we kept minimum diameter of the concrete specimen should be at least 75 mm. Then rod diameter, we need to calculate using matching the impedance with the specimen, and also restricting the stress in the transmission bar as 30% of the yield strength. So, we want to make sure that both the incident bar and transmitted bar has to remain always elastic. So the stresses cannot go more than 30% of its yield strength. So, and we try to keep specimen diameter very approximately close to that of bar diameter, and the specimen thickness, we try to keep it small to avoid the inertia effects and dispersion of the waves. So how to achieve the uniform stress state in the specimen? And usually uniform stress state is achieved only, like I said, after 4 reflections. So also the rise time of this incident pulse has to be increased, and duration and shape of this incident loading pulse is usually influenced by the geometry of the striker, novel striker, or you have to put some energy absorbing material at the impact end. So that's what we call that as a pulse shaper. So we have this novel striker. So basically the striker can be same as that of the bar diameter. Or you can also play with the shape of the striker so that you can achieve the uniform stress state, and also by increasing the rise time of the pulse. And we can achieve that by putting some energy absorbing material here. And mostly adopted technique is conventionally adopted technique is called pulse shaping technique, so that we get the uniform stress state. So what we really do, if without pulse shaping, if I'm looking at the strain history on the incident bar, you see here that the pulse is basically, you have this lot of this high frequency oscillations are there. Okay, and also I need to when I use pulse shaping, then I get this kind of a nice trapezoidal. You get this nice kind of strain history with a very high rise time. So you can see here that these kind of oscillations are all eliminated by using pulse shaping. These are all some of the challenges, because you need to achieve dynamic equilibrium and you need to get uniform stress state. So we need to play with these parameters to achieve the exact uniform stress state. And also we have to be very careful about what is the maximum strain rate that you can apply using this setup. So this maximum achievable strain rate is the strain rate beyond which the specimen experiences. If I apply more than this rate, then the material will not be in uniform stress state. It will be under non-uniform stress state. And the duration of the incident pulse or the specimen length, then it has to be limited to achieve uniform stress state. So basically, for a particular setup, for a particular striker diameter, for a particular pressure range that you're releasing, there is always a maximum cap on the strain rate that you can apply. So that can be calculated using what is the strain of the strain at failure of the specimen, and wave speed in the bar, and length of the specimen, and so on. So for example, if I want a material to undergo maximum strain of 1%, for that, and if I'm keeping length of the specimen as 75 mm and wave speed for the particular bar that you have chosen, it is, you can calculate that. So then we can calculate that the maximum strain rate for that particular setup is only about 111.67. Right. So like that we have to see. So, and again, alignment of the setup is also very important, and even a small deviation in alignment will adversely affect the results. And alignment tests are often conducted by, without putting any specimen. What we do is we directly start hitting the incident bar with the transmission bar without any specimen in between. And good alignment of the setup will not produce any reflected signal. So here you can see here. So this is your incident pulse, and this is your transmitted pulse. Okay, so but if you are having good alignment without any specimen, then you will not get any reflected pulse. If you are getting reflected pulse, means your alignment is not good. So we need to attach it. For example, this one you see here, this is doesn't have any reflected pulse. You get only incident and transmitted pulse. So that means it's very good. So this is our setup, that what we have. Like I said, this is basically the pressure accumulator, and you have a double acting valve, and this is a barrel through which the striker goes, And this is an incident bar. Again, it is a 3 meter. And then you have transmission bar. They're all supported on a nice, smooth, frictionless bearing. So these bars can move inside this bearing. And specimen is basically, before testing, what we do is we butt this incident bar and transmission bar and put the specimen in between. And these are all some of the specimens that we have tested: ordinary concrete, fiber reinforced concrete, and we tested specimen with the diameter of 100 mm, and thickness was about 50 mm. And we tested at different strain rates. One of the specimen you can see 54, 56. Actually, the static strength is only 28.4. You can see here, if I'm applying a strain rate of 55 average, then the strength has increased from 28 megapascal to almost 40 megapascal. Again, if the strain rate is increased to, let's say, 100, then this strength will become 40 to 50 or 60. Okay, these are all the things that you can find using this. Not only this strength, dynamic strength increase, also we can get the entire stress strain curve response itself. And similarly, fiber reinforced concrete, we add a lot of these steel fibers. And when these fibers were tested in quasi-static condition, under static load, you got strength of only 24. But when they were tested at 67 strain rate, I get a strength of 52. And when I'm testing at a 52 strain rate, I'm getting a 42. You can see here, with higher increase in strain rate, strength goes up. So that is exactly what we saw in the previous slides. So these are all the things that we have said. And this also, we tested some normal concrete. And you can see, you can get this kind of nice stress strain curve response. And the green color curve is the cylinder test that was done under very slow static loads. And these are your high strain rate. You can clearly see here that due to high strain rate, the strength increases, stiffness increases, and it is also failing at a larger strain. And how do you ensure that it is in dynamic equilibrium? Of course, you have to look at the characteristics of the test signal. And usually, if you look at incident plus reflected, should be equal to that of transmitted signal. Well, the testing is happening, right? And this is for fiber reinforced concrete. Again, for fiber reinforced concrete, at different strain rates, you can clearly see here that strength, stiffness, strain at failure, everything increase. So it is in line with what we have seen in the previous slides. And this is just one video. We used a very high-speed camera and tried to see how this crack is propagating. You can see here, right after when the reasoning goes, you will see a lot of these cracks that will develop, and the material will completely, it will get pulverized. Because you apply a very high strain rate. And we almost captured 50,000 frames per second. So you can see here that how the damage is happening. So these kind of high-speed camera systems can be used to see how the crack is propagating, on which side the crack is originating, and so on. And this is for ultra high performance concrete. I think we have also started doing a lot of tests on this, but this is the test result from literature for ultra high performance concrete. Again, why ultra high performance concrete? It is expected to perform well under high strain rate, which is for blast resistant applications, right? And here people have tried different fiber compositions, and they have also found that the peak strength increases with increase in the application of strain rate. Similarly, peak strain also increases with increase in strain rate. And this is what we talked about, dynamic strength increase factor for compression. You can see here that for very low strain rate, it is ranging at 1 only. But the moment your strain rate increases, you can see here that the dynamic increase factor also increases for UHPC. So that also people have established, like what they have established it for. And you can see at very high strain rate, you can clearly see that the material completely pulverizes. It becomes like a powder. But very low strain rate, you can see still it is not completely flat. If you are using a normal concrete, conventional concrete, even at very low strain rate, it would have gone to this thing. Because it's ultra high performance concrete, it was basically preventing this fragmentation and spalling for a very high strain rate. Right. So a quick summary of what we have discussed in this presentation. Ultra high performance concrete is basically, as you can see, in the last 150 years, the concrete has evolved over a period of time. We started with the Abraham's law: lower the water cement ratio, higher is the density, higher is the strength. So then people started developing using admixtures and high strength concrete. Then high performance concrete came. Now we are developing ultra high performance concrete. So it is a natural evolution in the development of concrete. And like we discussed, ultra high performance concrete is characterized by very high compressive and tensile strength, ductility, and durability. And because I have very high strength material, both in compression and tension, now I can design the structural members with very less size. So you end up with very reduced self-weight. And we can also go for longer spans. Once the self-weight is reduced, then for the same cross-section can be used for longer spans for the same external loads. And because it's a very densified mix, it does not let chloride or other deleterious substances or even water to basically permeate and reach the level of steel or rebar. So you end up with very good durability, and you also have lower life cycle cost. And cost of UHPC can be reduced by careful mix design using locally available material. The problem or disadvantage with UHPC is a lot of proprietary systems are available, but they're very costly. However, mix design can be developed just like what we designed concrete mix using locally available material. UHPC design mix also can be developed using locally available materials. And due to high energy absorption and strength, it is a very good material for impact and blast resistant applications. And a lot of research is right now happening on understanding this blast resistant and high strain rate behavior of ultra high performance concrete. Okay, so I would like to thank all of you for your patient listening. And these are some of the work that is done by MTech student and PhD student. And Dr. Syed is a collaborator. He helped us with establishing this split Hopkinson pressure bar setup. And I also taken some information from Professor Narayan and Nitlet's lecture. It is also available in YouTube. So I would like to acknowledge his resources as well. So with that, I will stop. And if there are any questions, I will be happy to. Right. So if you have any questions, so please feel free. I'll be happy to tell. Or you can also shoot me an email, and I will be happy. Let me see if there are any questions.
Thank you, sir.
Yeah, there are no specific codes available right now. There are Federal Highway Administration, some reports are available, but people are developing some design mix procedures. Okay, there are some research papers are all available, but there is no code per se available for developing the design mix. Yeah.
Sir, thank you very much, sir. Suriya Prakash, sir.
Thank you, madam.
Sir, I have a doubt, sir, small doubt.
Yeah,
what about the density, sir? Because coarse aggregate is not used, no, sir.
Right.
So what about the density, sir? Density will be less, no, sir?
Density will increase, madam, because you're packing more material, right? So density for regular concrete, you're talking about 2,400 kilogram per meter cube, right?
Yes, sir.
This one, depending upon your mix design, it can go as high as 2,000, 2,500 or 2,600. About 100 kilogram per meter cube, it will increase depending upon how your mix is. Density will increase. Okay. Yeah.
Okay. Sir, one more question, sir. It is in the chat box.
Okay. Let me see.
As the specimen is subjected to plastic deformations, how the elastic modulus is considered?
No, we are getting the complete stress strain curve, right? So elastic modulus is only applicable in the elastic regime. Here, what I am getting is because I'm measuring from the wave propagation, the strain rate and strain from integration of strain rate, I get strain at the entire duration, right? The stresses and strain. So I get the entire stress strain curve. So wherever you want, you can get your secant modulus. Yeah. Right? So that we get this entire, like what we have here, we get the entire curve. So elastic modulus, you're measuring only in this regime, but I know what is happening for the entire regime. Okay, using this wave propagation principles.
Sir, cementitious additives can be added, sir, to sell this ultra high performance concrete.
Yeah, no. I mean, we are adding a lot of the supplementary cementitious material, right? So basically, like we said, we need to do, because the whole idea is you want to use particles of size ranging from 0.01 micrometer to as high as 3000, 4000 micrometer. But in different gradation. So then only I can pack them very well, right? So these are all the material that we use.
Fly ash cannot be used, sir, because
Fly ash also can be used. Fly ash also can be used. Fly ash size is also, more or less, similar to that of cement, right? That also, yes, definitely. I have not added here. Yeah, for example, here maybe in supplementary material, fly ash also usually we do add. Yes, you're right. So here, here you can see fly ash is also there.
okay. Sir, one query we got, sir, from the participant.
Okay.
Size effect, sir. Will size effect comes into effect?
No, this is
Because specific.
okay. Yeah, no, this is a material study. Okay, and that's why we have taken 100 mm so that your aggregate sizes are properly considered. I cannot go for a large size specimens. Then you will have dispersion effects. So okay, so right, so that cannot be considered. So that is one of the limitations. Yeah, we cannot go larger specimen size. Then accordingly, then you'll have dispersion effects. Then your one-dimensional wave propagation assumption itself will not be correct. Right.
Sir, whether the heat of hydration will be same as that of normal concrete, sir?
See here we are putting. To be honest with you, it is expected to be high because you're using a lot of cement, right? And so it is expected to be high, but I don't have exact numbers. How much high it will be.
Sir, here one more question, sir. Mixing three types, since in mixing three types of concrete, HPC, SSC, and FRP, can we omit cement as far as
Okay, oh, you're talking completely getting rid of cement. So no, that cannot be, because unless you're talking about like geopolymer concrete, then it is very different, right? You need to have some binder, and binder here is cement and other supplementary cementitious material, but mostly it is cement. Because I need very high strength, right? I need to have reaction products also that should form very quickly, right? Yeah, let me look at it. What are the difference? Oh, okay, we are using. Oh, yeah. Well, the only difference between UHFRC and UHPC is even in just a terminology. When you put fiber in general, UHPC also will have 1 to 2% of steel fibers. You can go even 3% also. So this is just a terminology how people call it.
Sir, which zone of fine aggregate we use in UHPC? It is asked by participants, sir.
Zone per se, we try to use very fine. I think, let me see the particle size distribution. You can see here the size, anywhere it is ranging from about, I would say, 70 micrometer to as high as 2000 micrometer. So accordingly, you can see the zone. And we also try to use even ultra fine sand, because the whole idea is you want to use particles of different size so that you can all pack them well, right? So here we are just, because silica film is very like 1 micrometer, and sand here in this case I can also use ultra fine sand, so that can also, the size can be even smaller than that also. So depending upon what you are choosing, okay? But we want to limit the size of your aggregate. If you go for larger size aggregate, then you will lose flowability, because you're using a lot of cement, lot of fibers, then the flowability will be affected. So we want to be careful about the size of the aggregate that we limit. Okay.
Okay, sir. Thank you very much, sir.
All right. Thank you, madam. Thank you for all the
It is
participants.
an enlightening session, very informative, sir. It is actually an emerging area, sir.
Right.
Hopefully, participant got good inputs from your session, sir. Thank you so much In
Thank you,
spite of
thank
your
you,
busy
madam.
schedule as head, you have given the time and you explained about ultra high performance concrete, sir. Thank you so much, sir.
Thank you very much, madam. I would like to thank all the participants for patient listening. If you need any additional information, please send out an email. Then I can share you the material that what I have. Okay, all right. Thank you, everyone. Thank you. Thank you.
Thank you so much, sir.
Bye.
Yeah. Now the participants, it is a tea break from 11:30 to 12. Okay, 12 o'clock again join back. As I can see that before 5 minutes also some of the participants are joining. Please don't do that. We said already, based on the random like screenshot only we are considering